I don't know about you, but if I were you, I'd be exhausted hearing me. But I'm happy to try to take over and present you some of the material Jean-Jacques had in mind. I'm not 100% knowledgeable of everything you wanted to say, but I think I can go pretty much most of it. So first, let me introduce Jean-Jacques. He's been involved with crypto longer than I have, which is maybe 5 to 7 years before me. He came to the world of crypto, and he's been extensively involved, working in academia, working in industry with Philips research for 20 years, teaching at Université Catholique Louvain for 20 years. He has 20 patents, including the Quisquater zero-knowledge algorithm. He has worked on standardization with ISO. He has taught at ENS Rue d'Ulm. He has tons of publications in crypto and security. And so for all these reasons, he's a very good source of information. So the talk is broken in two pieces. A first part is about history of Bitcoin, and the second part is about history of zero knowledge. Now, the Bitcoin part is definitely the one part I'm less knowledgeable, so maybe you can fill in the gaps. But the paper about Bitcoin was published, I think, in 2004. And it's interesting to notice that the word blockchain is not used anywhere in this paper. 2000 what? 8. Okay. So the closest thing to blockchain is a notion of one-time chain of blocks, but the wording blockchain was never used, and it's not clear at all when blockchain actually appears in wording. And Jean-Jacques has no clue, and I don't know anybody who actually knows. However, definitely this cover on The Economist is a turning point where the wording blockchain became very popular and a lot of people used it. Now, there's this timeline, which is now Bitcoin sits here, midway between 2005 and 2010, and the vertical line shows a number of contributions and their timeline that ultimately led to Bitcoin and its successors. So one timeline is for time-stamping mechanisms, which start with Merkle tree in the 80s, and some of the ideas of Merkle trees, which is to use hash functions in particular cryptographic ways, were taken over by Habers and Stornetta around 1990, and in 91, Benello and Demare applied some of these principles to voting. Now, Habers and Stornetta is really the basic idea of time-stamping that's recycled by Bitcoin. And they actually obtained a patent for this, which, by coincidence, finished by now its lifespan. So the patent that could have benefited them financially for this invention died before actually Bitcoin existed and made it very interesting to tons of people. Now, another timeline is for digital cash. Digital cash was already mentioned in the early 80s, mainly to the work of David Chaum. And there was a few early contributions, but again, these things did not really catch on. They were available in the literature, crypto people knew about them, but people out there didn't really think much about that. Another timeline is for proof of work. Proof of work came much later, well, in a relative scale. Anti-spam mechanisms were invented, and ideas of proving work before you can get something came as early as the 1980s. Fault tolerance through Byzantine agreement came in the early 80s. That's one of the ingredients used in Bitcoin. Anonymous communication using public keys as identity was used for anonymous communication, again by Schaum, as early as the early 80s. And a lot of that followed on. And the notion of smart contracts came in the early 90s. And pretty much all these notions are combined into Bitcoin and their successors like Ethereum. So basically what Jean-Jacques wanted to show here is that something magic happened with Bitcoin, because pretty much everything needed to construct it was in the literature already. So about Merkle and hash functions and use for identity, there was just a few minutes ago discussion of Merkle trees, so I'm not going to go much into that. An interesting observation is that Jean-Jacques claims that there's a paper in the literature by Gévon in 1874, which basically has the same concepts and grind in it. If you read that paper, you can see that the basic ideas for this, and apparently some of it was actually related to factorization. This shows sometimes ideas can be much older than we think in this 1874 paper. So that's, I mean, I don't know this paper. I'm curious to go read it, so I suggest you do. That's the kind of reason I do such a talk. I learn things as well. And maybe because I'm mentioning, there's also a paper by, what's his name, Beautiful Mind? Nash. There's also a paper by Nash, which was classified for a very long time, and was around, it was earlier than information theory. And if you go read that paper with the idea of public key cryptography in mind, you can tell that what he's talking about is really public key cryptography. The words, you have to know what you're talking about to make sense of it, but clearly he had similar ideas. So there's interesting stuff out there in history. So the work that introduced the idea of proof of work was by Dwork and Naor in 1993, and they were using some proof of work principle to combat junk mail, where essentially you have to show, before you can actually get a mail delivered to someone, you have to prove yourself that you're worthy of having access to that mailbox, and you do that to a proof of work. And this is basically where the idea of proof of work came from. Now, electronic cash appeared in science fiction literature way before it was invented in reality, but the concept existed considerably before anybody did anything about it. The grandmaster of electronic cash is definitely David Schaum, who spent most of his student life inventing notions around electronic cash and how to implement things like that. I'm not going to hide that I worked with David at some point around these years, 85, 86. And I mean, he had tremendous ideas, which he eventually turned into a business called DigiCash. And I mean, the short reason why DigiCash didn't do it is basically because the world was not ready. I mean, this was way too early. Nobody knew of so many things. Nobody had that much interest in DigiCash. They could have sold to Microsoft for tons of money, but it ended up differently. And DigiCash went bankrupt after so many years. Jean-Jacques mentions there was an Esprit project, a European project called Café, with security digital payment system. And many of these people are still in crypto today. People like Michael Wiedner, Barry Schumacher, Torben Pedersen, Ronald Kramer. So tons of people were involved with this project, but it had a very rough life because this was still at a time where European Commission did not like cryptography. So encryption was sort of a devil. And whenever your projects mentioned that you wanted to do encryption somehow, somehow funding left to another room. And so that project had also very important stuff in it, but it's very little known because the funding died at some point. So that's a comic about the early days of blockchain that you can read at some point. I'll let you find it. Now, timestamping, Jean-Jacques draws this analogy of how did we do timestamping before we did it digitally. And he refers to the notion known in French as le cachet de la poste faisant foi. I have no idea what the English wording for it is, and he didn't either. But it's basically that when you put a stamp on a letter, the stamp that you just put on it is witnessing that it was handled by the post office on a certain day, essentially. And in many applications, you know, your paper was submitted at this time. Well, the stamp on the envelope would witness when you actually submitted it. Now, it's nice to know that, for instance, in the French jurisdiction, there's absolutely no guarantee at all that a stamp is going to be put on an envelope, and that if it is put in an envelope, there's absolutely no guarantee that it's the right date, and it's not even guaranteed that it's readable. So that's the kind of thing he said. So this was sort of the state of the art about timestamping before crypto got involved in it. And this is an example where it's absolutely unreadable what the time actually is, but there's strictly no guarantee. Yes?
It's in English, date as per postmark.
Okay, date as per postmark. I almost got that right. Then there's the analogy of a ledger in relation to posting information on a public board. And he indicates that this is sort of the premise behind the public ledger of blockchain, where if you just have stuff posted on the board like that, you have no clue what came first, you have no time sequence here, you can add a chain to it, and frankly, I'm not sure what he means here. So if one of you has a physical idea, I mean, is he gonna tie these to the notes, or, I mean, I would do it in a way analogous to Merkle. Whenever I put a new note, I would take a picture of the whole board and put that on my note so that people can see what was on the board before me and so on. But basically, if you connect them in a non-removable way, it indicates the sequence, not exactly when they came, but the relation between them. And he also suggests a more secure way where only people with the key can access the board as a mechanism to prevent that the orders be changed. Now, in the world where we digitize documents, hash functions are a good mechanism to create this linkage by applying the hash function to the content, and the hash value so created can be used as a reference that this document existed at the time where we created a new document. So if you put that hash in a later document as part of the document, unless you can break the hash function, you cannot reverse time. You needed that value before you created the new document. Now, he also draws an analogy with papers on spike. You can insert stuff on the spike, and it should prevent you from removing stuff and moving them around, so the standard stuff doesn't do much security for that, but there are more subtle ones. I mean, what does that do? Well, it's easy to get a piece of paper in and put it down, but if you want to remove everything and reorder them, you can't do that in one shot. You have to move things up, remove a little bit, move things. So the process of undoing it is time consuming. So it's analogous in that sense that this was sort of doing a one-way function, that putting stuff in is easy, but putting stuff out is a lot more expensive. Now, of course, another aspect of the Bitcoin is that it's decentralized, and so there's a number of models for the internet. That's an old thing, but it took a long time before it was actually implemented in the internet, and so a peer-to-peer solution could not have been really meaningful in the 80s or the 90s because peer-to-peer networks were not really of any existence or use back then. So he goes about the Habers-Stornetta paper a little bit more. Their first paper was in 1991. It introduced a method for timestamping digital documents, and it basically used the idea of extracting a hash from a document and using that in the next one and creating a chain with these documents. And I remember back then that they were suggesting that every week there would be a hash of the whole week worth of the chain in the New York Times, for instance. So there would be once a week, a trusted, mandatory responsible for posting the hash of the week in the New York Times, and everybody could look at it. So this was not yet quite as good as what came ultimately into Bitcoin, but this other paper by Benello and Demare was doing a broadcast timestamp, and their solution was very close to what ultimately came into Bitcoin. Now, I must say as a personal comment that when Bitcoin started becoming popular, I felt really uncomfortable because I knew that everything in there was sort of known already, and I had no clue how suddenly this attracted so many people. It sort of puzzled me, how is this possible? That all this stuff has been around for all these years, people in the community know these things, but then suddenly, I don't know. I mean, sometimes things just happen. You have no idea why. I mean, there are some explanations, but I still felt very strange about this because people were asking me, oh, what's this business? Well, it's based on a paper of 20 years ago and this other paper of 15 years ago. And I know all the people who invented these, but I have no clue who this guy is. And it's just funny. I think the marketing was really good. So this is the old original paper, and this is the patent which died not so long ago. Now Jean-Jacques goes about mentioning the voting work, which is based on the other work published previously. Now there's the Chinese Lotto thing. I kept it because I want to know, does anybody know what the Chinese Lotto problem is? I have no idea. So somehow it relates to some early proof of works, and Jean-Jacques mentions that there's a paper by him and Desmet which is related to this Chinese Lotto problem. I have no idea. I looked up in Google before I lecture, but there's so many references to actual Chinese Lotto systems that I couldn't find anything cryptographic in here. So anyway, so there was a Belgian timesec project which was for timestamping. And Jean-Jacques, together with Bart Prenell, was involved in this. This was between 96 and 98. And it was somewhat improving over Stuart Habers' work. Stuart was actually involved with them to getting this project ready. It used two hash functions in parallel, and it was proposed as an ISO standard. And it was also proposed as an Internet Engineering Task Force. I had to write this because I didn't know what IETF meant, I have to admit. So here is a few papers that Jean-Jacques published between 97 and 99, most of which are related to blockchain technologies and so on, but of course under different names. But if you look at all these things, there's not such a big gap between those things and what ultimately became blockchain. So there was even some consideration about the granularity and the scalability, which is very closely related to what ultimately was used. Now, another interesting aspect that I didn't know is that in 2001, there was a report written by the Bank of Japan where 7 existing timestamping systems, including timesec and of course the work of Haber and Benello, were compared. And it addressed the problem of a distributed consensus and how something like that could be constructed. And it was, in a sense, kind of asking for a proposal like Bitcoin to come up. It sort of paved the way. Go that way, it sounds reasonable and interesting. Now, this is the report, and there's some observation here that is saying that it should be such that a system that uses, that do not use trusted third parties are hard to implement because it would require complicated multi-users to generate timestamps cooperation, but this is really what Bitcoin ultimately did. Now, Jean-Jacques has some interesting remarks about the authors of that report, as well as the author of Bitcoin. The people behind the report were mainly Masashi Une and Tsutomu Matsumoto, and they somehow contain important components of the name Satoshi Nakamoto, who is the theoretical inventor of Bitcoin, because nobody knows who he is. So he was very puzzled by this relation. And moreover, he noticed that one of the references in the Bitcoin paper has a Satoshi as one of the authors as well. So he speculates. In particular, one of the two authors, Une, majored in experimental economy, and his research subject was cryptography linked to financial services. So this person would be extremely well trained to come up with something like Bitcoin. And in the paper, out of the 8 references, so that's a very short set of references, but it's right to the point. 5 of them refer to Habers, to Merkle, and to Jean-Jacques. Well, one actually refers to Jean-Jacques. And something that really puzzles him is that the citation to his work is not to the most commonly known version of the paper, but a very exclusive 40-participant conference in Benelux. And Jean-Jacques wonders whether this theoretical author was one of the participants to this event. So this is the paper, the Symposium on Information Theory in the Benelux, 1999. And somehow very few people know about this paper. So he was really puzzled how... Sorry? This? Okay. So anyway, why was it not invented earlier? Essentially because people didn't think it was important yet. People didn't understand things like distributed computation, peer-to-peer. I mean, there was no BitTorrent back then, no Napster, no Gnutella. All these things did not exist. So even if someone had thought about it, nobody would know what it meant. So this created some momentum for Bitcoin to be made. This created a background that made the things available. And then Bitcoin arrived and people saw blockchain inside, and then suddenly this older material became totally relevant, but somehow it got connected with Bitcoin, and people didn't know that much about the origin of this work. So this was introduced as an ISO project, and I'm just going to move on. I'll give you access to this list of standards which are related to blockchain recently. Now, as for the zero knowledge part, I'm going to be brief here because a lot of the material here was actually repetition of what I did this morning, so I'm able to cut down considerably. Now, one thing that I didn't do this morning, and I had questioned during lunch, so definitely this should be mentioned. Why do people like zero knowledge? Why do people want to use zero knowledge? And the main reason is for identification. When I go to a teller machine with a bank card, it's a really horrible identification mechanism because I put my card in the teller machine and then it tells me, please type your PIN, and then I type my PIN. Now, I'm a fool because I've never seen this machine before. I'm at a bank I've never heard of before. I'm giving away my PIN to total strangers. This is like the most absurd, useless identification mechanism. Everyone is supposed to trust any teller machine from any bank, even from any merchant. I mean, so zero knowledge is sort of the answer to that. So that we can do a mechanism for identification where we're not giving away anything that they can reuse and claiming they're me. So that's the basic point of zero knowledge, and the whole construct definitions and everything was around this idea in the first place. Now, ultimately, it became more applicable to other things, proving very complex things, proving in zero knowledge that something has a number of properties without disclosing it and so on. That's a lot more than identification, but it really started from identification. Now, you can imagine that this can be used in very many contexts, users to a computer system, driver to a card to a bank terminal, and so on. And now that we have smartphones, it's a joke to implement these things. I mean, honestly, I don't really know how things like Apple Pay and so on, applications from your phone work, but I suspect they use zero knowledge proofs in there. If they don't, they're total fools. But I do suspect they do that because it shouldn't be giving away your password or PIN code when talking to a teller machine. It should just prove that it knows who you are, it knows the password, but doesn't give it away. So the goal is to avoid the copying, stealing of the password, and also to prevent that the password gets stolen during the communication. So from the verifier side, we cannot trust terminals. We never know if we're talking to a real one or not. And we may need to speak to several terminals for verification. I have no idea what this means. Doesn't matter. So a simple solution is one-time passwords. If each time I identified, my password would be changed, and then whoever identified me allowed me to create a new password for next time, and that changed all the time, that would already be better. It would not be perfect, because if I speak to a fraud, then I would exchange a new password with the fraud, and when I go to my real bank, I would no longer have the valid password to my account. But that's less of a problem somehow. But it's not a super solution either, because it requires that we do mutual identification so that I can trust and so on. So zero knowledge is really an excellent solution to this. Okay. Jean-Jacques was involved with smart card from the beginning of smart card, and one of his achievements was to get zero knowledge proofs to go to smart cards. And many smart card systems do use zero knowledge proofs. They're not necessarily super duper, because the amount of computing to use things like large numbers and so on is difficult, but smart card have been implementing things like that for a while. That I'm just going to skip. By now, zero knowledge proof, you know pretty much what they are. They give you the ability to prove that you know a secret without giving the secret away. So you only involve the secret in some internal computation, and whatever you see from the outside, it does not automatically allow you to discover the secret. So Jean-Jacques is in particular known for one invention that he did with Guillou, which is the famous example of the cave of Alibaba as an explanation of interactive proofs and zero-knowledge proofs. So the setup is the following. This here is the cave of Alibaba, and this is the entrance to the whole thing. And there's actually a secret passage in this place. And there's a magic word that Alibaba can tell so that the gate between these two ends open. He wants to convince another party that indeed he knows the password to the cave. So first, the verifier is allowed to walk in here and look at the whole thing carefully. And this is the view of the other party. He sees that it's closed here, and he doesn't know how to go through it. Now, Alibaba wants to convince the other party that he knows how to open it, but he doesn't want to tell him the secret words. So, you have Alibaba and the verifier at the entrance here, and then Alibaba walks into the cave and goes either to point C or point D. And when that is done, the verifier moves down to position B. Now the verifier shouts, I want you to come out on the left side, or I want you to come out on the right side. Now, because Alibaba knows how to open this door, he can come out either way. If he's on the D side and he's asked to come out on the D side, he just comes this way. And if he's asked to come out on the C side, he just opens the door with the secret word and comes out that way. So that's essentially what this is describing, what I just told you. Now, if each time they try that and that the observer asks randomly to come out from the C side or the D side, and every time Alibaba comes out the way that he's asked, ultimately the verifier is going to be convinced that Alibaba actually knows how to go from C to D, but without having learned anything about the content of the password. So that's an example that works with children and all your family. Now, applications of zero knowledge by now are very many. It applies to all these authentication and identification mechanisms, but also for proving complicated statements of data that we don't want to disclose. Now, the limitations have some interesting, funny names. One of them is known as the grandmaster problem, and another one is known as the mafia problem. The grandmaster problem is you have a child who is playing chess against two grandmasters and convince them, well, they have a bet that the child is going to win against one of the grandmasters. And how does the child do that? Well, the child gets one grandmaster to play a move, and then it takes this move and plays it on the other board against the other grandmaster, and then the other grandmasters answer back, and this move is... So basically the child in the grandmaster problem is just acting between the two grandmasters. The child doesn't know anything about chess and is using the two grandmasters one against the other. And the mafia problem is essentially the same thing in zero knowledge context. If you have real-time connection between a terminal at one place and another ATM and another place, well, you can get people to prove their identity to another terminal if you can replay the questions from this terminal to the other terminal who asked the card, and so on. So the limitation is that somehow we need some mechanism to make sure that when you are interacting in a zero-knowledge proof, you really are interacting with whoever is asking the questions. And if this person or this object is referring the question from someone else and returning the answers to someone else, you may be identifying to another party without knowing it. And that's a limitation of zero-knowledge proofs, and there's a number of papers discussing this kind of issue. Now, I'm not going to show you the details, but this is the Quisquater protocol for zero-knowledge identification. It's based on the RSA assumption. It's not zero knowledge in the strongest sense, but it's zero knowledge in the model where you believe in hash functions, and we don't know of any efficient way of distinguishing the conversations so produced, but we don't have a reduction to a very well-known problem. But this protocol has been used in very many smart cards, and Jean-Jacques is and should be very proud of it. But I'll let you go check in the literature. I'm basically going to stop here. So this is a number of references that sort of started the work of zero knowledge. And that's going to be the end of my false identification as Jean-Jacques Quisquater. I should have changed to a French accent, but I completely forgot. I'm sorry.